Welcome back to the class on electrical machines too. In this lecture, we are going to discuss about the principal operation of a three-phase induction motor. In the last class, already we have seen the construction of a three-phase induction motor. Principal operation of a three-phase induction motor. In case of induction motor, the stator winding is consisting of a three-phase winding, which is displaced in a space by 120 degrees. On the rotor bars are there; those are short circuited. The stator winding may connected in a star and delta. Outside, we have three terminals. For these three terminals, we apply the three-phase supply. Whenever the three-phase currents are passing through the three-phase winding, which are displaced from 120 degrees in a space, the rotating field is created. The magnitude of the flux is constant. These red lines are nothing but a flux that will be rotating in a space. So in this manner, that flux will be rotating in a space, which is creating from the stator. That is a constant flux. The flux lines are always the closed lines. So whenever this rotating flux is creating from the stator, there is a rate of change of flux linkage with the rotor conductors. The voltage will be induced in rotor bars, nothing but a rotor conductors. That voltage will be driving a current through the conductors. Whenever current carrying conductor places magnetic field, it experiences a force. Every conductor is experiencing a force. All these forces collectively producing a torque at a shaft, so that the rotor also will be rotating in the same direction of the flux. This way. Now the flux and rotor also will be rotating in the same direction. So the relative speed between the rotor conductors and flux will be decreases. Because the flux is rotating with a synchronous speed, whereas rotor is rotating with a some amount of speed, the same direction of the flux. So whenever the relative speed is decreasing, the voltage induced in the rotor conductor also will be decreasing. The current also will be decreasing. The developed torque rotor also will be decreasing. The rotor structure is trying to catch the speed of a synchronous speed, but it never catches the synchronous. Because suppose the rotor is catching the speed of a synchronous speed, the relative speed between the flux and the rotor conductors will be zero. The voltage induced in the rotor conductors will be zero. The current also the zero. The developed torque in a rotor will be zero. Once it is zero, now the speed of the motor will be backs the synchronous speed. So in this manner, the rotor is always trying to catch the speed of a stator flux, but it never catches the speed of a stator. This is the basic principle operation of a induction motor. Now we are going to see slip. It is a very important term in a induction motor. Slip is defined as it is a difference between the synchronous speed of a stator flux to the motor speed. Already we have seen that the stator flux is running in one direction. The same direction the rotor also will be rotating, but the rotor never catches the speed of a stator. There is some lagging between the stator flux and the rotor. That means the rotor slips back the stator flux. In this case, the motor speed is nothing but a rotor speed. The difference between the synchronous speed and the motor speed is nothing but a slip. It is denoted by letter S. Generally, the slip of the induction motor is represented in terms of a percentage. Let's take the synchronous speed is ns. The actual speed of a motor is n. Now the slip of the induction motor equal to ns minus n. So the percentage slip equal to ns minus n by ns into 100. We are going to find out what is the range of the slip of the induction. Suppose the motor speed n equal to ns. In this equation, we substitute the n equal to ns. We are getting the value slip of the induction motor is 0. At the time of starting, the speed of the induction motor is n equal to 0. In place of n, if you substitute the n equal to 0, then the slip becomes a 1. So the slip of the induction motor will be vary between the 0 to the 1. The slip is never equal to the 0. The slip of the induction motor is 0 means the rotor also will be rotating at a synchronous speed. It does not happen in case of a induction motor. There are two conditions are there in an induction motor. One is the standstill condition, nothing but starting and running condition. Now here we are going to examine the sum of the rotor parameters. In this case, rotor parameters are nothing but rotor voltage, rotor frequency, rotor resistance, rotor leakage react. These four parameters we are going to discuss at two different conditions. One is the starting and running condition. At the time of starting, the speed of a induction motor is 0. The voltage induced in rotor is depending on the rate of change of flux linkage, which is directly proportional to the relative speed between the stator flux and the rotor stress. At the time of starting, the flux what is creating from the stator only rotating in a space, while the rotor is stationary. The relative speed between the stator flux and the rotor is the ns. How much magnitude of voltage induced in a rotor bar, that is highly depending upon the relative speed. So the per phase voltage at a standstill E2 proportional to the ns. It is also depending upon the remaining parameter, but those parameters are constant from the standstill condition to the running condition. So we can say very easily that the rotor voltage is directly proportional to the relative speed between the stator flux and the rotor. Now one more important parameter is the rotor frequency. See here the flux is rotating. We are assuming that the rotor is stationary. If the flux is completing the one rotation, then one cycle of the voltage will be induced in the rotor. Nothing but at the time of starting, the rotor frequency is equal to the stator frequency. The frequency of the voltage induced in a rotor, the standstill condition that we have taken is F2, that is proportional to the synchronous speed, nothing but the speed at which the flux is rotating, that is equal to the F. F is nothing but a stator frequency. Next, per phase rotor resistance is independent of the relative speed. Already we know that the resistance of the rotor conductors are always depending upon the length of the conductor, the cross section area of the conductor, what type of material we are using, but it is not depending upon the relative speed between the stator flux and the rotor structure. It is independent. Next, per phase rotor leakage reactance. Now, what is meant by leakage reactance means when the current is passing through the rotor bars, there is some amount of flux is creating from the rotor bars also. That is linking with the wound turns. Nothing but a rotor conductors has a some amount of inductance. That inductance is nothing but a LR, rotor inductance. That should be multiplied with a 2 pi F2, where F2 is nothing but a the frequency in the rotor at the time of starting. This is equal to the supply frequency. So the per phase rotor leakage reactance X2 equal to 2 pi F2 LR. It is highly depending upon the inductance of the rotor conductors, that is also fixed once the design of the motor is over, but it also depending upon the what is the frequency of the voltage induced in the rotor conductor. Now in case of running condition, already we know that when the flux is rotating in a space, the rotor also will be rotating in the same direction of the flux. Now the relative speed between the flux and the rotor conductors will be decreases because both are running in the same direction. Now the voltage induced in the rotor bar is directly proportional to the relative speed. The per phase voltage induced in rotor in a running condition, ER is directly proportional to the NS minus N. The frequency of the voltage induced in a rotor bar is also proportional to the relative speed, that is NS minus N. Next, third parameter is the rotor reactance in a running condition, that we represent as XR, that is equal to 2 pi. This is not F2, FR into LR. Already we know that FR is nothing but a frequency in running condition, that is depending upon the relative speed. So per phase rotor reactance also directly proportional to the relative speed. Now we are going to find out what is the relation between the rotor parameters during the stationary condition, nothing but a standstill condition, and running condition. The per phase voltage induced in running condition, ER is directly proportional to the NS minus N, that we have to take as equation 1. The per phase voltage induced in a rotor at a standstill condition, that is ER is directly proportional to the ES. Now take the ratio between equation 1 to the 2, ER by E2, that is equal to NS minus N by NS. This is nothing but a slip of the induction motor. So the per phase rotor voltage due to the running condition ER equal to S into E2, where E2 is nothing but a per phase voltage induced rotor at a standstill condition. The rotor frequency in running condition, FR is directly proportional to the NS minus N, that is the equation 3. The rotor frequency at the standstill condition, that is F2 directly proportional to the NS. Now this you take it as equation 3 and equation 4. Take the ratio between the equation 3 to the equation 4. We are getting the FR by F2 equal to NS minus N by NS. Again this quantity becomes a slip. So FR equal to nothing but the frequency of the voltage induced in the rotor is equal to slip times the the frequency of the voltage induced in rotor at the time of starting. The per phase rotor reactance in a running condition, XR is directly proportional to the Ns minus N. The per phase rotor reactance at a standstill condition, X2 is directly proportional to the Ns. Again, this equation you take it as a 5, this equation you take it as 6. Take the ratio between the equation 5 to the 6. XR by X2, that is equal to Ns minus N by Ns. Again, this is slip. So, the per phase rotor reactance in a running condition equal to S times the per phase rotor reactance in a standstill condition. The summary of rotor parameter. See here we are going to see the three different parameters at a standstill condition as well as running condition. The first one is the per phase rotor voltage. At standstill condition we have taken as E2, that is directly proportional to the Ns. In a running condition, the per phase rotor voltage here equal to S times the E2. The second one is the rotor frequency. At a standstill condition, the rotor frequency is equal to the supply frequency, but in running condition, the rotor frequency equal to slip times the rotor frequency at the time of standstill condition, that is equal to the supply frequency. This is F2. Third one is the per phase rotor reactance. The per phase rotor reactance at the time of standstill condition we have taken as X2. Running condition XR equal to X into X. So one more parameter is there, rotor resistance. The rotor resistance is independent of the relative speed between the stator flux and the rotor. Thank you very much. If you have any doubt, you can ask me directly or you can ask in the comment box of the YouTube channel so that I am always available to answer all those.